Okay, she gets applause. That's very nice to be encouraging. So, hello to the YouTube streamers, hello to the Zoomers. Can you all hear me and see me okay? Excellent. Let me get a question or just waving. Can't tell. I'm getting the screen share going. That's the next step. Okay, do we have a question from the Zoomers or just waving? Oh, okay, just look that we're waving. All right, cool. Well then, all right, let me make sure the recording's going. I'm always paranoid about that. Nope, we got it. Okay. You ready?
Ready as I'll ever be.
All right, Hillary's going to walk us through your second formative assessment. We've got the scores for both sections here simultaneously, so you can see how things went for folks. On the whole, very well, actually. So really no big surprises, no complaints, but we just want to make sure that you're understanding, if you missed something, why that is the case.
Yep, exactly. So yeah, folks did really well on the whole. There were maybe like 2 questions where most people, even on those 2 questions, most people still got the right answer, but there was enough variation that we'll dive into it a little more. But first up, and I'll just have y'all jump in with some answers for this. So the correct label we can see is the fixed intercept. With these ones, it's kind of straightforward, right? Are there any questions about the fixed intercept? Everyone got it across the board, so I don't want to spend a lot of time. All right, and then the definition. Someone tell me why they chose what they chose for the definition of the fixed intercept. And most of you got it right, so I know that, like, we know what it is. But just to help make sure that other folks are also following. Why is it the expected outcome when the predictor is 0? Because that's what Lisa said the definition was. Great answer, yes.
Because math, I would also accept.
Yes, because math is also a good answer. Yeah, basically beta 0 or your fixed intercept is always whatever y is when your x or x's are 0. Let me see, where are we over here? Y'all got this one pretty much right. This beta 1 is a fixed slope. So still fixed, but it's not an intercept anymore, it's a slope. And then, as usual, a slope is change in y per 1 unit change of x, right? That's our 8th grade definition that we've been talking about. So no surprises there. I imagine that folks who did miss questions on this mostly just need to read the question another time, honestly, which is a very normal thing, right? We know that E sub I is the error, right? Can somebody tell me conceptually what that means? I just want to be sure that that wasn't a question next. Like, what is E? What does it represent in our model?
How off the prediction is from what actually happened.
Yeah. So there's our nice line that we predict, right? And then here's where we are, but our line predicted we were here. All of that in between right there is the error. But it's summed up over all of them, right? Thank you. Okay. So, again, this was great. So, the correct interpretation of 80 would be the expected enthusiasm for school when hours of Nintendo equals 0. These are basically just application questions from our definitions earlier. So, -2 for every additional hour of Nintendo, enthusiasm for school is predicted to be lower by 2. Again, our standard slope. No surprises there. Okay, before I move on here, I want to stop, because this is one we're going to dig into a minute.
Yep.
Maybe more than a minute. But are there any questions, comments, points of clarification on the vocabulary sorts of things before we do this? Okay. I'm trying to watch the chat.
Yeah, I'm
So-
watching too, so.
Yeah. Sometimes you need a minute to type. My fingers don't go that fast. All right. So for this one, those of you who got it right, explain to me how you figured it out. And I would like to hear from at least 3 people, because there's different ways that you can think about this and still get the right answer, right?
Yeah.
So, let's aim for 3. Oh, Jenny, yes, if your hand is actually up. Sometimes Zoom automatically picks up on it. So,
No, I did that.
Okay.
Okay, this is so dumb, but I actually drew the graph ninth grade algebra style and then kind of moved the origin over by 10 units to figure. Because I think I was originally doing the same thing that caused people to think that 80 would become 100, and I had a feeling it was not right, so.
yeah. For the record, that is an excellent strategy. When you are in doubt, draw it out. There's nothing that will help solidify it like drawing the picture. So great work there. Especially when you feel like, well, I don't think I'm getting the right answer. Drawing it out is a great strategy. Other folks want to share how they got there.
I did it similarly, just without the visual. So if x is 0 and the intercept is 80, I looked at my slope and saw my slope was negative. So I know I'm going to be going down as I move to the right on the graph. And so I know I'm moving over 10 predictor units to recenter my intercept. And so the new intercept is going to be whatever the prediction would be at that spot. And so I took 10 times the -2 to get -20 and subtracted that from my original intercept, which gave me 60.
Yep.
Great.
Great. One more person, then I can move on to my part and we can carry on with our class. Anybody? Anyone?
You could ask about then why the -2 is wrong.
That is true.
Why does that one not change?
But the slope doesn't change?
Exactly.
Where you are when the slope changes?
Exactly. The slope doesn't change in this because we're not touching that at all. We're not messing with any of the relationships in the data. All that we're doing is adjusting our scale. We're kind of moving it along in terms of where we're going to put our 0. And so I think about it like zeroing a scale, right? Like if you were at the grocery store and you were going to get some bulk items and you had a glass jar, you put your glass jar on there and you hit the zeroing function. That's kind of a similar thing to what we're doing with
I like
this.
that. I've never thought of it that way. Oh, okay. That's good.
Yes.
Well, steal that.
All right, absolutely.
Okay, thanks.
Full permission. So, yeah. And then when we do this, there's kind of like two aspects, a tiny bit of foreshadowing of what we're probably going to talk about coming up. But in terms of just like solving the equation, we're setting x at 10 as our 0 point. So really, we just have to plug in that 10, replace our xi with 10, and then 10 times 2 taken from 80. And that's the math that will get us to where we need to be for solving it. The step that we'll be talking about more is centering your data coding-wise, where you're gonna actually take all of your numbers and subtract 10 from those in order to make the data be centered around that one point. But those are kind of two distinct things. So I think some folks, when they saw like x minus 10, may have plugged in minus 10 to the minus 2 and then thought that they needed to add it, right, with the algebra there. But that's a slightly different sort of process for making it be centered. Any questions on that?
Yeah, a question in the chat.
Oh, perfect. Yeah, I think I got confused with the term of centered at 0. And basically we're making, or at 10, sorry. We're making 10 the center. Like that's why we're calling it that. We're gonna make that our new 0 point and then use that as our like comparison. I don't know if that helps. Any other questions? Okay, great.
I would say like if
Yeah.
orange is the new black, then 10 is the new 0.
Yes.
That's how I would do it. Or if, orange is the new pink, then you're seriously disturbed. But that's a separate movie. Thank you for laughing at that.
Did you have a question?
I was gonna ask why you would center it at 10. Like, in my head, it makes
Yeah.
sense if like the average student, if you find that, a gross amount of the students have 10 hours, then it would make sense to center it there because
Yes.
that's kind of the baseline that you're
Mhm.
looking at.
Yeah. Basically, where you center is entirely arbitrary from the researcher's point of view. But the important piece about centering is to make your 0 meaningful. Like if we are dealing with education, right, and it's 0 to 16 or whatever, 0 education is not a meaningful sort of way to interpret anything because it's not very realistic in the US context, especially, that someone has truly 0 education, right? And so the whole point behind centering is to make it something meaningful so that you can interpret what you're getting more easily and more kind of intuitively. Anything to add, Lisa?
Yeah, I would say at this stage, it only changes the fixed intercept, but in more advanced models with interaction terms, then it actually changes the other slopes too. And so because I know that's coming, I'm setting it up from the get-go.
Could folks on Zoom hear that? What Lisa was saying?
Yeah, I got the
Okay,
good mic
great.
today, so I hope so.
Okay, good.
Okay, good.
Great. All right, so we can move on. Y'all did great with this question. The only point for clarification is that when you've got binary sort of data, it tells you how 1 differs from 0, not vice versa.
Yep.
So the 0 group here is public schools, and so this tells you how Montessori school is different from the public school value. But that's not exactly the same as vice versa. Okay, and then for these next couple questions about standard errors, one important thing is make sure that you are reading, because I think some folks just kind of glazed over it and didn't pick it all up. which is fine. We're all humans. We do that. I did that when I did the first round of this. So, you know, it happens. So the standard error for a mean, what would it indicate? Someone want to explain to me why they answered what they did. For 5 is expected difference on average for an obtained sample mean relative to the corresponding population mean. And then also, how is that answer different than some of the others? Because I think those are important for understanding what we're getting at.
Are you
Yes, do it. Whatever it is.
Are you enjoying your training on managing awkward silences?
Oh, y'all don't know this, but I am a professional at awkward silences. I used to have to transport people who didn't speak English, sometimes over very long distances, and we simply could not talk to each other, so there was no choice but awkward silence. So I can do this all day, but it's not fun, right? Like, it is awkward, it's uncomfortable, so it's just better to speak up, and well, because most of you got it, especially, right? Like, it's one thing if I'm asking you something super hard, but for the easy stuff that you got right, why not claim that victory publicly? And you're like, no.
I was just gonna say, I like to think of it like kind of the graph where like if you kind of have like a larger set of like students, it's gonna start like shrinking down more. So it's like, you know, you're gonna have like that kind of like sampling of like 5 differences amongst each other. So that's like one way I thought of it.
Mm-hmm. Yeah. Visualization is a great tool. Like, if you can call to mind like the differences between like a big sample where you have everything kind of neatly here, and then a smaller sample where things are gonna be more all over the place, like, that's a helpful visual to keep in mind, especially when we're thinking about a couple questions ahead from now. So let me see, where are we? So yeah, I think when I was looking at it, make sure mean. So any of the ones that said sample slope, automatically out of the race, because we're not talking about the slope in this one. And then the other piece is, are we talking about people's values, or are we talking about sample mean values, right? So someone put that together for me.
You got an answer in
another
the
one.
chat that does, I think.
Yes, okay, great, yes. The second answer choice describes the standard deviation. Exactly. So standard deviations are related to like just one sample and the way that the people within that sample are different. Standard error is kind of like a standard deviation of samples as a whole.
That's exactly what it is.
So just make sure that you're paying attention to those small differences in some of these going forward. And then this one is basically the same question, but it's for a slope. Your slope can also have a standard error, and does have a standard error, right? So, things to keep in mind. And it's the sample slope, not the individuals. All right. So, in order to get a smaller standard error, which is usually what we're aiming for, we don't want to have a ton of noise and craziness in our sample. We want it to be kind of straightforward. So why is lesser remaining outcome variability and or a larger sample size going to get us that smaller standard error?
Doesn't a larger sample size get you closer to the true mean or something like that? No.
So not necessarily, because like when you have that normal distribution, you never know if your sample is in the tail. Like you could end up by pure chance with that weird sample that is way off. But the probability of that is like super duper small. You know, depending on where you're at in the p-value, right, that's associated with it. But I think you're kind of on the right track. So maybe think it out a little bit more if you're comfortable doing
Well,
that.
so I get bigger the sample size, and it reduces our margin for error, but I can't say exactly why, just because we have more of it. That's all I got.
Yeah, I mean, as we have a bigger sample size, we kind of minimize that noisiness of it, right? So no one weird person can throw everything off quite as badly, right? If you've got 100 other people that are not so weird, right? So that's one way to think about it. Other comments on that?
Just with the idea that if we have a larger sample, it will be more accurate, so that reflects the standard error. We could be more accurate with that,
So
or with everything.
we want to be more accurate. That's our goal. But we really don't know where our sample is in the whole like sampling distribution, right? So I don't think that we can say that it's more accurate with a larger sample, but I do think we can say, well, we know mathematically, right, that like that's, you know, it's all divided by the square root of n, right? Or is it n?
That's it for the
Is
mean.
that-
For a slope, the
Slope.
variance of the predictor is part of that too. On the
Yeah.
bottom.
Yeah. Okay. But a important factor in determining the standard error is your sample size. So as like something in your denominator goes up, you're going to end up with something smaller on the whole, all else there, or all else equal, right? If you just hold those things constant. So that might be a simpler way just to think about it.
Yeah, I think how I'd reconcile it is I would say with more people, your results become more predictable. Like
Yeah.
what the range of possibility is kind of squishes in until it's sort of dancing around one number more so. But we don't know if it's the right number, like ever, because the population is sort of a mythical construct that we don't have access to. So I think it's how representative your sample is of the population would dictate more whether you're right. And that's more of a judgment call than it is like a math thing. But I think it is true that the more people you get, the more consistency you get across repeated samples of the same kind. Whether
Yeah.
your conversion to the right direction is a separate concern, but it's supposed to happen that way, theoretically. But it's not guaranteed.
Yeah.
Yeah.
And then the only other thing I'll say is that the remaining outcome variability is not something that we have any control over. Like, really, that's just kind of like whatever people give back to you and what your model produces, you know, like you can, yeah. It is what it is. And so that's why we focus a lot on
You can have
controlling what
predictors.
we can,
Yeah.
which is our sample size and our predictors, right? But, all right, that's it. Thus concludes your time with me today. And your awkward silence with me, yeah.
What I want to ask is out of those options. So as for formatted assessment, I retake it after being graded because I want to make sure I know all the correct answer. but now it's marked as late.
Oh,
So
okay.
I would like to ask, would it be a problem, like, am I losing my credit?
Nope.
Mark as late.
No.
No, and that actually brings me to a point I forgot to mention. So if you answer everything incorrect, you get 3 points. Okay, so just disregard what it says in icon in terms of your scores are. I have a separate spreadsheet where I look and see, did you do it? 3 points for you. So yes, if you want to go to extra trouble to retake it to make sure you understand, thank you. Why would I possibly penalize that effort with late points?
Yeah.
Good.
Yep.
Yes, and yeah, I did set them up hopefully so you can see your scores this time. Everybody can see everything? Yes, so thank you, Hillary, for that. Very nice. Yeah, I did not intend to hide them from you. I just forgot that I had to hit post after I hit open, like there was an extra step involved. So hopefully you can all see what you answered, see your scores, and you get your 3 points for giving it a try. All right, then let's see. What else do I need to talk about? Let me get to the course webpage and remind myself. This is the problem of teaching 2 courses. It's like, who did I tell what? Okay, you turned in homework. You have, we just did FA2. Oh, that's right, you have FA3 for next week. So since we have a lot of abstract concepts and letters and things like that, we're going to do another round of practice with this before I attempt to do it on a homework. But what I did want to start doing is showing you how to actually make Stata and R spit out these numbers. Like, where did the numbers come from that I put in the PowerPoint slides? That's what I wanted to show you, is the behind the scenes part of that. And also to remind folks that next week I am out of town and we are losing access to this classroom on the 2nd anyway for comprehensive exams. But Hillary has offered to do office hours during class on Zoom. And are your office hours after this class anyway, or is that Thursdays or Tuesdays?
Wait, yes, on Tuesdays.
On Tuesdays,
they're
not
after this class.
Okay, so that way you can get any questions answered that you have. Let's see where we are. And then we'll have homework to do. So if we don't get through everything that I need you to know for homework 2, I will push it back 2 days though. That way you at least have a full week after we finish something before you are responsible for it. All right, yeah. That's all I wanted to say about that. Am I forgetting anything? Don't think so? Are you excited to see some software? Said no one ever. Are you excited to learn tangible skills that can help you get a job someday?
Yeah.
Okay, there we go. That's the right pitch. So by now, all of you should have started what I would refer to as a technical skills section of your CV, in which any kind of research software that you know how to use would be written down. Qualitative, web production, anything like that, these packages can go there. So you can list that you have beginning experience in R, or you can become proficient or expert or whatnot. So yeah, for real, and no matter where you're headed and what you want to do, having more skills to manage data can be a very useful thing. So example 2, so this handout is posted on the website. There's also a zip folder of the original source files. Does everybody find this, or do I need to show you where it is? We're good? Zoomers, we're good? Good? Good enough? Okay. All right, then. The story here is the General Social Survey data set that I borrowed from 2012. That's why the numbers are a bit off. We are going to be predicting annual income in thousands of dollars. So income is our outcome. Quick quiz in my notation. What letter do I use for outcomes, X or Y? Y. What letter do I use for predictors? X. Okay, cough, cough, formative assessment question. We have a quantitative predictor for years of education, and we have a binary predictor for whether or not a given participant in the study is married. So I am going to show you how to fit models as well as to obtain additional pieces of information, which I call linear combinations of fixed effects. How do you get your output to generate additional useful things? That's what I want to show you, because this is something I didn't learn nearly soon enough. So I'm going to go through in order. I have Stata code, and then I have R code. And then I have Stata code and output, and then I have R code and output. So you get a break if you only want to learn one package, but it's also a good thing to try and pick up multiple packages. That way you have the flexibility to work with whomever, with whatever kind of data. And that's 2 programs you can put on your technical skills section. So starting with the Stata code then, first things first is to tell Stata where your files are. So for instance, this is where my work directory is for this class. If I want to access Stata using the virtual desktop and use one of my local folders rather than the remote folders, I have to put this in front of it. So this is something I demonstrated in the example 1 videos, but I just wanted to remind folks that there is that necessary prefix if you are accessing local folders from your Stata in the university desktop, virtual desktop. I am importing an Excel sheet. So Stata has an engine that's designed to do that. You just need to feed it additional pieces of information. So anything in red like this that's in quotes in Stata is case and space sensitive. So check your spelling if it yells at you and because it can't find your file or can't find your variable. In Excel, you can have multiple sheets of data to tell it which one you want to pull from. There is a sheet option. Case preserve means keep whatever pattern of capital and lowercase letters are in the variables. By default, it will make them all lowercase. Read the first names. The first row as names is an option, and then clear means if it's already there, go ahead and re-import it. So let's say that you import your data, you try to build a new variable by centering, and you screw it up. Could happen, right? We're imperfect people. No worries. If you accidentally remove a column or write over a column and you need to get your original data set back, all you need to do is rerun this, and it will pop back up into memory, and then you can do things with it. So don't worry that you've somehow screwed things up, because your Excel file will be safe and sound in your directory, and it's the active memory inside Stata that you have messed up. But you don't need to save it. It will just go away at the end of the session, and there's no harm, no foul. Because I was taught to be a responsible data analyst, I always add variable labels to my variables. So these are extended pieces of information that append in the file so that anyone looking at your variables would have a better sense as to what they are. In R, I want to point out that in order to run this, you need to have installed and loaded these packages. So these are additional add-ons to our software that other people have written to do things. There's millions of them. There's a place called CRAN. I don't know what it stands for. CRAN is the acronym. That's where they're all hosted. People also put them on GitHub. So it's just a question of finding a package that does what you need to, installing it, and loading it. The code that I wrote checks to see if it's installed, installs it if not, and loads it otherwise. So the ones that we're using are listed right here. Set working directory is how you tell R where your stuff is. So this is where it is on mine, and I have a note that relative to what I'm used to seeing for Windows, that the backslashes are the wrong way. So if you type this manually, beware of that. There is a function I borrowed called read Excel from the read Excel package. You just want to know what the file name is, what the name of the sheet is. Same thing in here. Anything in quotes is case and space sensitive. Sometimes when you import files into R, they show up as different kinds of data than what we can use. So that I never have to worry about that, I always have a line in here to make sure that my data is stored as a data frame, which is what it needs to be in order to do analyses in most cases. And R does not allow you to add labels for a lot of functions, and so I did not bother to do that. All right, so first things first, if I have a data set, I need to understand my variables. So what you did for homework 1, that's what we're going to do now, because running descriptives can help you understand what is possible and whether your data are accurate. So summarize is the command in Stata. Display just means print this to your output window. So this is a title that I wrote. You don't have to write this, but future you might appreciate it if you write titles for what you're doing. So I have my 3 variables that I'm interested in that are quantitative variables. Mary is a binary one. So this is for income in thousands. We've looked at this before. So my mean for income in thousands is 17,000 in this data set, 17. Has a variance of 190, and that is standard deviation squared. Education has a mean of 13.8 and a standard deviation of 3. So on average, people went to almost 14 years of school, but any one person would be expected to be off from that by about 3. That's the standard deviation for education as one of our predictors. And then marital status is currently coded 1 versus 2. So there's nothing wrong with that, but it's not truly binary yet. Binary means 0 and 1, so we'll have to address that. The mean is 1.46, which means about 46% of the sample is married, according to that. In R, for descriptive statistics, I am using a function called describe that is from the psych package because it spits out a bunch of things that I would want at the same time. So the code is a little more involved to use R relative to stata. But X is the name of my data set here. And then within the data set, what do I want? Is the brackets. Now I have a space here. And words like, hey, you have an extra space, but I left it here. That means use all the rows. So like the bracket is essentially guiding it in terms of rows and columns, what you want to summarize over. If you want all of your data, then you would leave this space and put a comma right here. So the empty thing means use all the rows. After that, which columns you want are inside this little function here, C, which means either concatenate or combine, take your pick. And I'm saying I would like these 3 variables to be summarized. Case and space sensitive for these as well. Fast equals true means don't put a bunch of other stuff in there that takes a little longer. And then last but not least, because the default output did not give me enough precision, I took this entire describe thing and I stuck it inside a print function. So right here, that much, that's describe. What I'm asking it to print is the results of what's highlighted right now. And then comma, digits equals 3 means 3 digits after the decimal. And you can see that it didn't obey that for all the columns, but it did for the ones that we need that. So if you ever don't get enough digits, you can wrap your results in a print function to do so. I have an option at the top of my R file to add more digits to everything, but not all functions obey it. Some people's don't, just 'cause. Var is how we can get variances, and this little table here has a special name. I don't know if you would have heard this name before. Have you heard of a variance-covariance matrix? No? Okay, strip that from your memory. You don't need that for this class, it's fine. But in general, when you see a little table like this, on the diagonal, it looks like I have a variable with itself for income, for education, and for Mary. Those are the variables variances. And in the off diagonal are what is known as covariances, which are unstandardized correlations. So variance-covariance matrices like this get used in the advanced classes for multi-level modeling, structural equation modeling, and factor analysis, but they won't have a big deal in this class. But so you've seen it before. All right, our very first model. Are you ready?
Yeah.
Like, yeah, this is it. This little thing right there, that's it. It's empty. Empty means no predictors. So we're just estimating the naive starting point for predicting income. If I know nothing else about a person, what am I going to get? This is more of a pedagogical exercise than a real one. I'll tell you that, in this class at least. So the empty model is our starting point. It's the most naive prediction in which everyone is expected to have beta 0 as their predicted income. So the colors here I'm using deliberately. Red is for fixed effects. These are estimated values that are constant across people that the model returns for us. What's E? What's that represent? The error, or synonym starting with an R? Residual, yeah. And E is how wrong we are. So E is how far off your outcome is from what the model says it should be. Right now, the model just says your outcome should be the mean. So this is as much offness as we would have. So the variance of these E's that we're going to see is the variance of the variable. It's all error right now. That number we had in our output up here descriptively was, let me find it again, 190.209. That's the variance of income in this sample. Let's find that in our output. So first stata, then R. The only command really that we're going to use for about 95% of the time this semester is regress. Can you guess what that stands for? Regression, yeah, it's like the verb, regress. When statisticians say that, they say regress y on x. That language to me is backwards. So you're going to hear me say x predicts y, and that will be the end of the word regress in my vocabulary. So Stata code is really, really short, and you have to just sort of assume you know how it works. Like there's no signposting. So that's both good and bad. You're just supposed to know that the first word after regress is the name of your outcome. And that is true for all Stata functions as far as I know. Hillary, can you think of any that don't have the y as the next thing?
It always assumes that the first variable is your y.
Yep. So the first word should be the name of a column that you want to predict, and it is case and space sensitive, but it's not in quotes. The comma differentiates options in terms of what you want printed for this model. So level 95, I'm asking for confidence intervals at 95% confidence. That means what is my alpha going to be? What alpha corresponds to 95% confident? 0.05. So yeah, think of it either way. We're saying that 5% of the time is what we're going to define as unexpected. So we have a 95% confidence interval for the range in which our result is expected to fall. We have then a few new pieces of things here. So here's a table on the left, here's a little table on the right, and then here's a third table down below. You can ignore all of this for right now, except for this one number, that one. That's why it's in bold. You see the word residual? That's your key. This right here is our variance of the e's. It is going to be called residual variance. Where the rest of these numbers come from, I will explain later. It's not relevant right now. Root mean square error. Can you guess what that is relative to 190? It's the square root, so that's the standard deviation. So from this perspective, we're saying how wrong is the model? Oh, it's 190 wrong. How wrong is each person's score predicted to be? Like off by 14 on average. So root mean square error, or residual, means offness, wrongness. And at this point, it's all wrong because we're not predicting with anything. We're just saying, let everybody have the mean and call it good. What does that mean? 17. So coefficient is the answer. That is the value that collectively made the e's the smallest. That's how we know what it is. So here's our standard error. So this goes by two different names. You can think of it as the standard error of the mean, because that's what this represents at this stage. More generally, this is the standard error of the fixed intercept, which is labeled as underscore CONS in Stata for the constant. So on average, people make $17,000. The expected inconsistency across samples is that 17 would be off from the population mean by about 0.51 on average. And so that offness, if we had a larger sample, would shrink even further. If we had more variability, it would expand. Where did T come from? That's my next row over. T is 34. It's like, so? My question is, where did 34 come from? The follow-up will be, will we care? How do we get a T? We're reviewing this. This is last week's fun. Zoomers, I'm watching the chat.
You test it against a null hypothesis.
So if we say the null is 0, 17 minus 0, that's the top of it.
Doesn't matter because the 0 doesn't mean anything.
Yeah, not in this context. Like, Is 17 different than 0? Well, I'd hope so, because that means on average people make no money. That's what the null hypothesis would say. That seems really depressing. So it's not necessarily an interesting hypothesis, but just to walk through the table. Where'd the 34 come from? There we go, divided by the standard error. So this is a general principle. Coefficient divided by standard error is t. What is the probability of observing a t this large if the null hypothesis is 0? It is 0 to 3 decimal places. Said differently, this mean of 17 is 34 standard errors away from the null hypothesis of 0. So we can soundly reject the null hypothesis that people make no money on average. Do I care? Nope, but that's what it means. And here's the confidence interval that would go around that. I gotta get it right. The range in which the population value would be contained 95% of the time. Does that sound right? She's nodding. This is when I have to literally read my own definition because confidence intervals make no sense to me. But they're at the end of the output because a lot of times people want to see them. Here's R. Good news for R folks. LM is pretty much the only thing we need this semester too. So Stata is regress, R is LM. Do you know what LM stands for? It does. Have you seen it before? You have not? You just took a lucky guess? Linear model. The other thing that is really lucky is that LM is a base R function, which means it's not something that some dude made that can possibly have screwed it up, or chick for that matter. Screwing up code is gender neutral. But it is something that is built into R that we don't have to worry about quality control, is my point. A lot of people's R code that you will find online does not name their arguments, which I think is terrible practice, and so you will see my code being a little bit longer than others so that it's clearer. The first argument, an argument, by the way, is a coding term. It means piece of information the function needs to run. What data set are we using? This is called example 2. So for instance, when you start homework 2, this would need to be changed to whatever you called the homework 2 data set. Formula means what is my equation? With one catch. In R, arguments are defined using equal signs, which means my formula can't have an equal sign because it's already used for something else. So whoever made R is like, fine, I'll use squiggle. So tilde, I believe, it is the thing above the tab key on the left-hand side of your keyboard. I'm going to call it squiggle. And the 1 represents the fixed intercept. Because it's like, what variables do you have in the model? Well, it's kind of like I'm saying I have an implicit 1 here, that everybody has a 1 so that everybody gets a beta 0 contribution to their score. That's what it means. In the matrix equations for these models, you have a columns of 1 to make the multiplication work out. So the 1 there is to represent that idea. It's a default in Stata, so you don't have to write anything, but I add it in R for my own edification. So the default output for R, I don't like for this, and so I'm adding some things to it that help. I found a package called Supernova. That's a very dramatic name. Someone wrote it to go with another person's regression textbook. So I am saving the results of my analysis to an R object that is called model empty. So this is my name. I write things in title case. You can name this whatever you'd like, so long as there's no spaces and it doesn't start with a number. So like you could name this I hate R, and it would be fine with that. Although then you'd have to pick another one like, I hate R a lot, like for your next model. Because if you write over it, then it will undo your work. So you want to pick different names, but you can pick whatever names you would like. I'm going to go with model empty. So if you just run this much, you won't see anything happen. You actually have to ask it for the results. It doesn't get printed by default. So the first result I'm going to ask for is a repackaging of it so that I get a table that looks a lot like what it did in Stata. And I'm going to give the same caveat. You can ignore everything. Look, there's literally nothing in here. You can ignore it. 190, same thing here. We have MS and then total in this case because that's what it actually represents, is all the total variability. In R, summary is how you ask for the default model output, and what you want the summary of is the name of your model. So that gives me this much. 17 is the mean. We found that in Stata. Note that it's called estimate. What's the difference between an estimate and a coefficient? Nothing. It's a semantic distinction. It's just how people choose to label things. Estimate and coefficient mean the same thing. Next column over. Standard error. That one has a similar name. Next column over. T-value. Similar. And this one, p-value. This is scientific notation. That means it is 0 to like 16 decimal places. You can shut that off in R as well. I have it set to use zeros up until it hits 9 and then switch to scientific notation. Residual standard error. That is the standard deviation of the e's. That's the same thing as root mean square error according to Stata. And then last but not least, I asked for confint, which is confidence intervals at the level of 0.95. So I had to ask for 3 different things in order to get the same information that shows up by default in Stata. Okay, with me so far? So this model sucks. It's the worst model you can have. It says everybody gets the same income and that's it. We can do better, right? We can do better than nothing. So I'm going to add education. So now how many fixed effects do I have in my model? 2. Meaning how many different terms have to get found in order to make this work? Beta 0, beta 1. So I have prompts here for us to complete what these things mean. So first, Stata output and then R output. Education is now the second word in here. That means it's a predictor. You're supposed to know that. Guess what happens if you switch them? Do you get the same thing? You do not. I'm mentioning this because at least 3 of you is going to do this one on your first homework, if based on past data. What happens?
It switches the outcome and the predictor.
Yep. If I write it this way, education is being predicted by income. Now, conceptually, that's the answer to the same question as to how they're related, but that will not be the case once there's multiple predictors. So we don't want to do that. So this is answering a research question, to what extent is income predicted by years of education? That's what we want to know right now. So now my table has numbers in it. You can still ignore everything except this one. MS residual has been reduced from 190 to 162. Is that good news or bad news that it went down? Good news? Yeah, we would call that explained variance. All of the reasons why some people make more money was 190. Now all the reasons why some people still make more money after controlling for education is 162. So some of it is due to education. How much of it actually is given over here? That is going to form the basis of what is going to be called R square. So 15% actually. We have a 15% reduction. 15% of all the reasons why some people make more money is because of their education, and 85% is meh, don't know yet. So 162 here is the amount of leftover variability. 162 is the variance of the e's, specifically in this equation, the e's part. The variance of y is still the 190. But now we're saying 15% of it was captured by this part, and 85% of it is still over here. Now what happened? My constant has a coefficient or estimate of negative 7.89. So my reference person is in debt. Weird? What might explain that? Who is my reference person? Person with zero education. Now that's not wrong, but it sure is weird. Pretty sure no one answered the general social survey with no education. And even if they did, they do not make negative $8,000 a year. So that's weird. We can fix it though. How about the slope for education? That is 1.82. What's it tell us?
For every year of education, you will make $1.82,000 more.
Exactly right. For every additional year of education, predicted income goes up by $1.82,000. So is this slope positive or negative? Not a trick, I swear. Positive. Okay, so that means if I ask you a question about a slope, you can rule out the answers that start with negative. That's all it's based on. It's just literally direction. So a positive slope means as x goes up, y goes up. A negative slope means as x goes up, y goes down. Standard error for my slope is 0.16. It's kind of small. Coefficient divided by my standard error is 11. So these are numbers we saw on the slides. So my slope is 11 standard errors away from a slope of 0. That's what T is telling me. It's locating my result on a standardized distribution where the mean is the null hypothesis and the standard deviation is whatever the standard error is. So like this is my unit of inconsistency. The standard error for the slope is 0.16. So on average, my slope of education will be off from the population slope by 0.16 across samples. The fact that it is 11 standard errors away from the mean means it doesn't really matter what my alpha level is, it's significant. And it's not a p-value of 0 stata, it's just less than 3 decimal places can show. So putting that together, we've described the slope as positive. Would I describe it as significant or non-significant? Significant. Do I reject the null or do I retain the null? Reject. So am I saying, yes, there's probably a relationship? Yes, looks like I have some evidence towards that, at least in this sample. The fact that this slope confidence interval does not overlap 0 corresponds to the idea that it's significant. So across repeated samples, you would usually find a slope that's above 0. In R, same deal. Adding in education as a predictor. 162 is now the magic number that tells me how much E-variance is left. I get the same information but in a different order. So note the fixed intercept in stata is always going to be given last in the table for reasons that are unclear to me. The fixed intercept in R output is always given first. Other than that, they will look a lot the same. So residual standard error is down to 12.7, meaning the average wrongness is less. R square it gives us as well, and then something else test about that we can skip for now. And here's our confidence intervals. So this is a weird result in the sense that you can't make negative $8,000. But it's a consequence of us not centering our predictor. So a lot of folks would center predictors at their sample means. There's totally nothing wrong with that. However, in this data set, the sample mean of education is 13.8. Do you think any person wrote that down as their answer in this survey? That they went to 13.8 years of education? They did not. It's not a thing. So somewhere in the middle that is a representative value is what I would recommend for variables that have inherent meaning like this. So I could pick 12, which is what I did, because that corresponds to a high school degree. I could pick 16 if I wanted that to correspond to a bachelor's degree, maybe 17 nowadays, 16 and a half, something like that. So somewhere in the middle, somewhere within the scale of the variable is what I would recommend for centering. And I will tell you what that should be in your homework as well. So if we answer the questions then, the intercept, that's my expected outcome when education is 0, because that's when this part of the model would go away. And then the slope of education is the change in income per unit education. So income is expected to go up by 1.82 thousand. The expected income for somebody with no education is the minus 7.89. If we fix it, we're going to center. That means add or subtract a constant so that you redefine what 0 is. So now, beta 0 changes its meaning. Beta 0 is still the expected value of y when the predictor x is 0. But now, when is x going to be 0? What kind of person? 12. Yeah, this zeroes out at 12. So that changes beta 0 to be specifically for someone with 12 years of education instead. But it does not change beta 1. So to do this in code is fairly straightforward. In Stata, the command to make a new variable is called gen. It stands for generate. There's also one called egen, which is for fancier things. We don't need a lot of those in this class. So when I create new variables, I always use the same type of naming convention, especially while teaching. The format of this is new equals old minus whatever constant. So educ is what the column is called in my current data set. 12 is what I want my new 0 to mean. So educ with the 12 at the end is what I decided to name my variable. So I am creating a brand new column that takes whatever was in the current education column and subtracts 12 from it. A lot of folks will do some kind of naming convention like this with an underscore and a C after it for centered. I don't do it that way because then I would have to remember what I centered it at. So this way, when I see this in my output, I know the meaning is 12 is 0. That's just a convention that I follow. So the difference then is I'm going to rerun the same model, but putting the 12 version of it in here. So in your first homework, your first model will be an empty model. Your second model will be a quantitative predictor that is centered at a constant. I will ask you for your second model for residual variance, and if you get that right, you know you have your model right. The next question will be for the fixed intercept. That means if you get that right, that you have the right centering for the predictors in your model. If you get residual variance right, but you get the intercept wrong, that means your variables are not centered at the right place, but you have the right variables. Because the definition of an intercept is when it's at 0. So if you have residual variance correct, your model is correct in terms of its contents. If you have the fixed intercept wrong, that means you've centered at the wrong 0. And usually what folks do is make themselves a new variable, but then forget to change it in the code. So that's an easy fix. In R, the code is a little bit longer, but same principle. This whole thing refers to first the data set, example 2, $, because someone's going to pay you if you learn R so they don't have to, and then the name of the new column, educ12, is from the old column, which is all of that, data set, $, name, and then minus the constant. There may be ways to write R code that you don't have to write out the name of the data set the whole time, but it's less transparent. So as I warned you at the beginning of this semester, my code is longer, but hopefully clearer. So let's fit education 12 in as the predictor instead. Same amount of variance left over. So we're not hacking anything. We're not cheating. We're just changing what 0 means so that the intercept changes. And then lo and behold, now who is my intercept for in my output? What kind of reference person? High school graduate is predicted to make $14,000 a year. What happens if I go to 13th grade after that?
Supposedly plus $1.8 thousand.
Supposedly, yes, an increase of $1,820. So yeah, the slope is the same. Centering does not change the relationship between an outcome and a predictor. Centering changes the reference point for the regression line. Where on the line are you starting from to talk about going up or down from? That's all. And here are the confidence intervals from that. Okay, how we doing? Now, what if I told you there's a way to make it tell you what the predicted income is for anybody? That's actually a fairly easy thing to ask for. Let me end with this, since it's 309. Here's our equation. That equation tells me what is expected for income for anybody, any level of education. I just got to plug in the value here. So according to this version of the variable, if I want to get predicted education for somebody who went to 20th grade, what would I have to plug in? And don't say 20. If I want to get predicted income for somebody who went to 20th grade, what do I have to put in the parentheses here? It's not 20 in this case because education is centered. If I want 20th grade and education 12 is my 0 point. 8, yes, this is the tricky part. Yep, it's 8 units above my reference of 12 is what 20th grade is. So this is what it would look like to get predictions for different kinds of people. For 8 years, I would plug in -4, because that's 4 less than 12. For exactly 12, I plug in a 0, that drops, and now you can see why the intercept is the expected outcome when x is 0, because this part cancels, and all you're left with is the fixed intercept. If I want 16 years, it's +4, and if I want 20 years, it's +8. So I can do this on a calculator just fine. But what if I want standard errors for each of these? I can do that on a calculator too, but it's a little more painful. So what's coming on Thursday then is walking you through code that gets you predictions for any kind of person you want. I will show you the long way, and then later in the semester I will show you the short way. Because once you understand what the code is doing, then you can take the shortcuts, but we'll do it the long way until we get to that point. Fair? Okay. 311. Any questions or comments before we call it a day? Are we feeling okay? Okay. If you feel anxious about the coding or the software, open the source files and just run them. Like try to regenerate these results and see, and you can match up where the numbers are. In the source files are also the full output. I've just pulled out the pieces that are relevant, but you can see all the rest of it too. And this is something the TAs are happy to help with. They can help you walk through things. If you want to practice with data that you care about, that's even better. We're happy to help with that as well. Okay, then it's garbage day. Happy garbage day, belatedly. So that means I say see you Thursday. And you can start working on your next formative assessment. So, thanks for being here. Bye for now. Bye, Zoomers. Bye, YouTubers.